Hello, I am Aul Salaf, and I will be your assembly language teacher. Assembly language is the language computers actually speak. When we talk Python or C or C++ or JavaScript to computers, there's a piece of software that translates that to assembly language, which is the actual language computers speak. Now, why would anyone want to know assembly language? First of all, you're not going to write large pieces of software in assembly language. That's basically not been done since the 80s and almost not been done since the 60s because it's a really bad idea. Assembly language is slow to write in. You have to pay a lot of attention to very small details, and we love Python. We love the compiler that does so much for us to make it easy for us to speak to computers. But understanding assembly is still very important because you're going to have complex bugs that you'll need to debug that go above your code into operating system code or driver code that somebody else wrote, and that's the only way you can understand it. Because you'll want to do security and you want to understand how code other people wrote works, so you can find flaws in it and fun stuff like that. Because sometimes you'll have a huge project that runs one small loop billions of times, and if you can get that small loop of 5 instructions to run 10% faster, that will mean saving a whole month on a computation that takes a year. So there's many reasons to want to know assembly language. Personally, the one I'm most passionate about is it's simply so beautiful. A friend of mine wrote a poetry book, only all the poems, instead of being written in English or his native Hebrew, or Chinese, which he also speaks, they were all written in assembly language, which is probably his favorite language. And I want to show you one of those poems. I will not explain it. Don't be afraid. By the end of our class, you understand all the assembly commands, and by the end of this short lesson, you'll understand in Python why the poem works. So let me just share my screen. Screen share. Entire screen share. So here you can see his poem. That's the link if anyone wants to look at it at home. It's very short, 1, 2, 3, 4, 5, 6 assembly instructions. And very cryptic, right? I've translated it to Python here into 1, 2, 3, 4, basically 4 commands. You have these also to help us keep track of it. And let's just see what this does. We're not going to understand line by line how it works, what these things mean, but just observe how at first we have 8200 in A and 1337 in B. Let's run this loop once. Now we'll have 9521 in A and 16 in B, and then we run it again and we have 9505 in A and 32 in B. And we run it again. After we run it a few times, B becomes 0 and A becomes 9537, which just happens to be 8200 plus 1337. So what this strange cryptic poem we don't understand does is it adds 2 numbers. And I'm promising you, it looks weird now, but by the end of this lesson, you'll understand how this piece of Python code works and why it will always print the sum of the 2 numbers and 0. So let's stop sharing the screen. Stop. Me again, Aul, as I said. In Hebrew, you spell my name Aleph, Aleph, Vav, Reish. There is no way to spell it in English. If you found one, there's a prize. Contest's been open, I think, for 6 years now. Nobody won it yet. And I served in Unit 8200. have a startup, I teach programming, it's cool. Do all other sorts of stuff. Assembly is one of my hobbies. I mostly do it at home. Sometimes I get hired to do a bit, but mostly a hobby, and I love teaching it because it's so beautiful. Last year, I had 2 days and they asked me to teach an assembly course that usually takes around 2 weeks. So surprisingly, we succeeded and we managed to transfer all the material we needed to teach. We were very tired and very surprised by the end of it. Naturally, this year, they asked me to add more material. So it's gonna be an interesting ride, a very demanding couple of days, and that's also why we have this preparation lesson. But we've tried it last year, it's possible. I trust you and I'll be there to help you. So don't worry, if you need any help, I'm here. After 2 days, I promise you, you will know this stuff, and you will know this stuff to the level we need you to. So we can teach you other awesome things in security and optimization that depend on it. First of all, I want to mention Python Tutor, this debugging tool we saw before. Actually, I'll not show it again, but it's available on pythontutor.com. I'll send you the link. It's very useful for doing the exercises, and in general, it's very useful for learning Python. So know that exists. And now let's get to our first topic. I'll just mention in this preparation lesson, we'll learn how to count. How to count with only 2 digits, because that's how computers count, and that's very important if you want to do anything related to how computers think. Yeah. So how do we count? Basically, humans started counting like this. Here's one more, here's another one. So here we have, as you see, this amount of things. Yesterday I went and hunted this amount of rabbits, and yeah, it was very tasty. Or yeah, yesterday I picked this amount of apples, but it's not very comfortable, right? Counting by just, we call it the unary method, where you just say, oh look, there's this amount of trees in my neighborhood. So pretty fast we invented more useful methods of counting, like for example, prisoner unary. You all know it. It's the way you count days to release, maybe days to the end of school. You've all met this. It's just like unary, only grouped visibly to be easier to look at. So obviously this is 17, right? You can see it at a glance. And that was nice, but eventually humans developed even better ways of counting. Like, for example, this one, right? You all know this, Roman numerals. This one is obviously 10 minus 1, which is 9, and this one is 10 plus 5 minus 1, which is 14. So that's a better way to count. Still not very useful. Try to do math with this. I mean, this plus this would be no very useful algorithm for doing math with this, right? So then the Indians invented Arab numerals, and we call them Arab numerals because the Arabs learned them from the Indians, and the Italian guy called Fibonacci learned them from an Arab guy called, sorry, I don't remember his name, and he taught it to all the medieval, all the Renaissance European guys, and today we know how to count, which has enabled us to do tons of things we couldn't do before, because counting is so important. Being able to efficiently calculate taxes and how many rabbits we have, or whatever. So you all know it, counting in decimal, right? 531. This one is how many hundreds we have, and this one is how many tens we have, and this one is how many ones we have. And you just say 5 times 100 plus 3 times 10 plus 1 times 1. And that's how many are in this number. And because of very basic properties of math, we can easily do addition with this. 531 plus 151 is 1 plus 1 is 2. This is 8 and this is 6. And if this was a 9, then it would get a bit more interesting. We have 9 plus 3, which is 11. And 11, and the 10 here plus 6 would be a 7. So that's how we do addition with this. You've all learned it in primary school. You all know it. No need to spend too much time on this. Now, why do we use 10 digits? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Why not 16 or 2 or 5 or 6? Legend says it's because we have 10 fingers. But computers have 2 fingers, or at least when you try to build electronic computers, it's much easier to represent 2 different states than to represent 10 different states. So when we deal with computers, it's much more comfortable to work in binary, where you say you have a ones digit, and what would be the analog of a tens digit? So this one is ones, and usually we have tens, which is the number of digits. Here would have the number of digits, which is 2. So this would be the 2's digit, and this would be the 10 times 10, 2 times 2, the 4's digit, and this would be the, and this would be the 8's digit. So what's this number written here? 1101 in binary. That's an 8 plus a 4 plus a 1. 8 plus 4, 12 plus 1. This is 13 in our usual decimal system. And that's how you count in binary. Actually counting is very easy. You start with 0, then you go to 1. Try to add another one, but you can't because you run out of digits. So 0 again, and you increase the next one. Then you have 1, 1. Once again, this is a 0. You try to increase this, reach a 0 again. Add a 1 here. Add 1. Once again, I need to increase this one. 1, 1, 1, and we're up to thousands, which are, so this is a 1's digit, 2's digit, 4's digit, 8's digit, so this is 8, right? This would be 7, which is 4 plus 2 plus 1. Okay, that's how we count in binary. Very simple, right? Nothing complicated about it. Just what would happen if humans had 2 digits instead of 10. And computers have 2 digits. Oh, I see. Half of my calculation doesn't fit the camera. Here's what I did. All right. Another very useful way of counting is hexadecimal, or base 16, where we have 16 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, this was invented very recently, and humans don't have symbols for representing a digit whose value is 10 or a digit whose value is 11. So the British, I think, people who invented this just say, let's use A for 10, B for 11, and that way until F for 15, right? If in base 10 the largest digit is 9, in base 16 the largest digit should be 15. So let's see if you can do this alone. I'll write a hex number, A9, D3, and you try to tell me how much this is in decimal. Any idea? So this one is just 3, right? It's the 1's digit, like we're used to. And this would be the 16th digit. D, we remember, is F minus 1, right? DF, so it's 14. 14 times 16, and this would be the 16 times 16, or 256 digit, and it's a 9. And then we have here A, which is 9 plus 1, 10, and it's the 256 times 16. Let's just call it 16 cubed. I don't even remember how much this is, but we can open a calculator, which we will do. Let's open a calculator. And all we need to do is write 10 times 16 times 16 times 16 plus 9 times 16 times 16 plus 14 times 16 plus 3. And let's ask Python to print this. And here we have the result, 43,491. So, not very complicated, right? It's mechanical. I wrote a huge number here, so obviously it's a bit hard, but it's not complicated. We count just like we do in normal numbers. You know, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 8, 9, A, B, C, D, E, F, 1, 0, 1, 1, 1, 2, 1, F, 2, 0, and then after we get to 9F, so it's A0, and then blah 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 until AF, and it's B0, and we know the way until FF, and then it's 1, 0, 0. Nothing surprising, just like we do it in decimal, only more digits. I'll explain later why hexadecimal is so useful, but just a hint, think how easy it is to convert between base 10 and base 100. The answer is very similar to that. Okay, next I want to talk a bit about addition. Addition in decimal, we all know, 3 to 6 plus 5 to 5. 6 plus 5 is 11, so that's a 1 here and another 1 here. 1 plus 2 plus 2 is 5. 3 plus 5 is 8. Addition in base 2 is just the same, 1, 0, 0, 1 plus 1, 1, 0, 0. So this is a 1, this is 0, this is a 1, this is a 0, but with a carry of 1, and we have 1, 0, 1, 0, 1. Let's try to check some by converting to decimal. So this is the 1's digit, 2's digit, 4's digit, and 8's digit. So 9 plus 8 plus 4 is 12, right? 9 plus 12 should be 11, 21, right? Yeah, 21. And here we have a 16th digit, so 16 plus 4 plus 1. 16 plus 5 is indeed 21. Same result. We know how to add binary. Does anyone guess how to add base 16 hexadecimal? Let's say 9A plus FF. Just like we'd expect, F plus A, that's 15 plus 10, 25, or 16 plus 9, right? So that's a 9 here. And we have 10 plus F again, 25, or 16 plus 9. Very simple, very easy. No need to speak about it too much. You all know how to add binary and how to add hexadecimal. Most of you, by now, should be able to understand that exercise we talked about before, the poem by my friend. If you want, you can go back there and try. But before that, I want to talk a bit about course exercises. Since we want to learn very fast, all exercises in this course will be debugging exercises. I'll give you a piece of code, like for example, let me just share my screen again. Pieces of code, like for example, this one. This is a piece of code that's supposed to convert binary to decimal. You have 0 is supposed to convert to 0, 1 is supposed to convert to 1, 1, 0, 0, 0 is supposed to convert to 8, 1, 0, 0, 1, of course, to 9. These are tests. The only problem is these tests are failing right now because there is a bug in this Python code. And what you need to do is copy this code to our friend Python Tutor, run it, examine it and figure out what's wrong, where's the bug, fix the bug, and hand in fixed code. By fixing this code, you also understand the process behind it, and you can be sure you understand how all these concepts work. So these are the exercises, and the way you hand them in is you go into this link. Oh, if I'll go into it here, you'll see my account, which is not good. You go into this link. Of course, don't copy the link from the video. We'll send you everything in text. But you go here, have some patience. Free servers are usually very slow, but eventually it will load. Then you create an account. Wow, it's especially slow today. Sorry. It's a video. You can skip a bit if you want. Look until you find the screen showing something more interesting than this. All right. You don't have an account, of course, so you sign up. This submission software was originally made for Teams, so just write your name both in the team, and this one should be ITC15, and the secret phrase is ITC15. You can write the same thing in the name in the user and the user's name if you want. You know, my name is Tila Ur, and you don't have to fill a phone number, but if you want to fill these things, it will help me help you, you know. I don't care about the number, I care more about email, so I can help you with stuff. And choose some password. I'll choose 1, 2, 3, 4. You don't need to fill in the other users. Again, you're single users, but it's meant originally for Teams, so just fill one user, submit it, and you'll have all of these exercises assigned. Choose the first one, B2D. I'll send you a zip file with all the exercises. Then you just open the exercise, find the solution. Of course, I won't show you the solution here, but you just paste the solution and submit it. We'll talk in class about how to hand in new versions if you had a mistake. But now that you've handed this in, if you'll go back, you'll see it's submitted. You can also see checked and other statuses here. Okay, so we finished talking about how to hand in exercises, which is important but boring. Sorry for wasting your time. And let's discuss some other interesting things relating to binary numbers. Let me just grab a cup of water first. You can fast forward the video. And I'm back. So our next subject would be converting. Let's see, we talked about, okay. Remember I told you there is an interesting reason computer scientists love hexadecimal? Let's talk about that now. If I asked you, how do you convert 101110100 into decimal, it would take quite some time to figure this out. There's all of these powers of 2 you need to figure out, additions and whatnot. But converting this to hexadecimal is very easy. All I do is separate it into groups of 4. There's a 0 here. And do the conversion separately for each of these. Why does that work? Let's think a bit about, as I say, decimal and base 100. If I had this number in decimal, 1, 2, 3, 4, and I wanted to convert it to base 100, so I need a digit saying how many units of 100 I have, and a digit saying how many hundreds of hundreds I have, right? So 1234 is 12 hundreds of hundreds plus 34. It's 12 hundreds, sorry, plus 24, plus 34. And if it were longer, it would still work, you know. Say 5, 6, never mind. So this could be the units, and this would be hundreds, and this would be 10,000s. It works. You just split it by digit, and conversion is very simple. On the other hand, writing this long thing on your keyboard takes a lot of time, takes a lot of space in email or code or wherever. But just writing, you know, 9, 10, 4 plus 1. 589 is a very simple thing, and short, concise to write in your email. So that's why computer scientists love binary and hex. And of course, the reverse translation is also very straightforward. You just take this digit, replace it with 1001, take this digit, replace it with 1010, and it works. Quick thing to cover. How do we do the reverse? Let's say we have binary, we have decimal 95. How do we convert 95 into binary? So we need to figure out how many 1s and how many 2s and how many 4s and how many 8s this number has. Figuring out how many 1s it has is very simple. If it's odd, it has a 1, 1. If it's even, it doesn't have a 1, right? So this is obviously odd, and therefore it has a 1. Now, what remains is 94. And if we shift 94 right by 1, we'd know just how many 2s it has by looking whether it was odd or not. But shifting it right is just, in decimal, it's like dividing by 10, right? So if we divide by 2, we would shift its binary form by 1. So divide this by 2, 94, this will be 45, sorry, and this will be 2, so 47. Right here we minus 1, and here we divide by 2. We get 47, which is odd, so another 1. 46, that's minus 1. Divide this by 2, 23. Another 1. I'll erase this so we have more space to work with. We have 22 remaining. Divided by 2, 11. Wow, so many odd numbers. I didn't plan this example. So that's another 1. We get 10. Finally, an even number. We can just write a 0 here. Divided by 10, we get 5. Odd, 4. Divided by 2, we get 2. Even, so we write a 0. Divided by 10, by 2, we get 1. And that's just our 1. So 1s, 2s, 4s, 8s, 16s, 32s, 64s, 128s. I made a mistake somewhere. I have too many digits. I should not have 128s. But the method works. Just look at whether the rightmost digit is even or odd. If it's odd, add a 1, otherwise add a 0, then divide by 2 and do it again until you're out of digits. And this method should always work. Don't trust my mistakes. Bonus to whoever looks at the video and emails me my mistake. Thank you. No time now. Let's talk a bit about module. Okay, basically we're done with all the basic stuff. Also, we're almost out of time. I just want to talk about how do we do negative numbers. So this is finally not something boring and basic, but an awesome math trick. And who doesn't like awesome math tricks, right? So let's think about, for a moment, about the way we do math on a clock. For example, someone says, it's now 2 o'clock, meet me in 15 hours. So what's 15 hours? 14, 13, 12, 11, 8. Eventually, after 12, we come back to the same place, and then we do another 2. So 2 plus 14 on the clock would be 4, right? And 2 plus 11 on the clock would be 1. You all know this again from primary school. Very simple, but very interesting, because let's say I wanted to subtract 1 using clock arithmetic, but I only have addition, I don't have subtraction. How do I do that? Just a moment. I'm with you. Clock subtraction, right? What do I need to add to any number on a clock to get that number minus 1? 11. 11, and it works, right? 2 plus 11 is 1. 5 plus 11 is 4. 12 plus 11 is 11. Everything works. And if I want to, let's say, multiply by minus 1, what does it mean to multiply by minus 1 actually? It means to get the number who, if I add that, I get the original 2. Okay, let's say I have this number. Multiplying by minus 1 means I want to get this number, right? Mm-hmm. Try it. Multiplying in a clock by 11 would always give you this. Just take a calculator, try it. This is called modular arithmetic. You've probably encountered it sometime in your computer studies, and it's very useful. And that's what's going to allow us to do negative numbers with computers. So the basic principle is this. Let's look at all the numbers they can represent, for example, with 2 bits. So they are 0, right? 1, 1, 0, and 1, 1, which are in decimal. They'd be 0, that's 0, 1, 2, and 3, right? But what if instead of calling this 3, I call it minus 1? Would addition still work? 0 plus 1 is 2. 0 plus 2, 0 plus 1 is 1, of course. 1 plus 2 is minus 1. That's strange, but it worked on the clock, right? 2 plus minus 1. 2 plus 3, that's 5, but we need to subtract 4 because we're in clock arithmetic, so we get 1, which is 2 minus 1. So this works. 0 plus minus 1 is 0 plus 1, 1 would be 1, 1, which is minus 1. 1 plus minus 1, 0, 1 plus 1, 1. So this is 0, 0, and we drop this digit, so we get 0. Yes, 1 plus minus 1 is 0. Modular arithmetic comes to our aid, and this seems to just work. So I can call this one minus 1 if I want, and I can even decide to call this one minus 2 instead of 2. Or if we had more digits, right? Let's say we had 3 digits, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Naturally, in what we call unsigned numbers, regular numbers, we call this 0, 1, 2, 3, 4, 5, 6, 7, right? But we could instead decide to call them 0, 1, 2, 3, minus 1, minus 2, minus 3, minus 4. And if you check it, arithmetic still works. You can add, you can subtract. It works just the same, and you just need to remember to drop any digits above 3. It works. It's amazing. It's a miracle, but it actually just works. And we could do the same, calling this 4 or calling this 5 and just having negatives until minus 2. Why do we decide to specifically take all these to be the positives and all these to be the negatives? For a very simple reason. That way we have a simple test of, is this a positive or negative number? If the leftmost bit is on, it's a 1, then it's negative, otherwise it's positive. And this seems to just work, everything is nice. I want to show a few properties of this representation. For example, how do we take a number and get its negative? How do we go from 3 to minus 3? So what we need to do, and you can explain why, it's very simple. First, we need to negate all the digits, so 0, 1, 1 becomes 1, 0, 0. And then we need to add 1, 1, 0, 1. And this always works. Let's take 1. So for another example, we start with 0, 0, 1, negate all its, 1, 1, 0, negate all its digits, add 1. 1, 1, 1 is minus 1, we won again. So the algorithm for getting the negative of a number, I should show that it works the other way around. 1, 1, 1, negate all its digits, add 1, and we won. It always works. It's very simple to explain why. You can see you can just look at the diagram and understand why. Of course, subtraction is very simple to implement. I want to subtract B from A, so I just take the negative of B and add it to A. For example, 2 minus minus 1. So I have 2, 0, 1, 0, and I want to subtract it from 1, 1, 1, which is minus 1. I'll take the negative of this, which we already agreed was 0, 0, 1. So we have 2 plus 0, 0, 1, which is 3. Just like we expected, because we know primary school arithmetic. This works. Everything works. Try it. I just want to mention, remember when I said negate all the digits? So there's a bunch of operations computer scientists like to do, which we do separately on each digit of a binary number. And you'll just need to know their names so that you can understand the poem from before, so that you can do the exercises and so that you can survive as a computer scientist. The most basic ones are called not, or, and exclusive or XOR. So not is a function of a single number, and it just negates the digits. So bitwise not, which is the kind of not we usually want to do, takes every digit of a number and negates it. For example, bitwise not of 10110, 10110 is 01001. And or is something that is a function of two numbers, two binary digits, which looks at them. If at least one of them is a 1, the result will be 1. Otherwise, the result will be 0. People like to draw the full function values, so the OR of this would be 0, 1, 1, 1. And let's take a more interesting example here. The OR of this would be 0, 1, 1, 1, 1. Because of this, because of this, because of both of them, and because of this. And this one's a 0 because it's none of them. Now we have AND, which is very similar to OR, but it's only 1 if both of them are 1. So let's look at an example for AND, 1, 0, 1, 1, and 1, 1, 0, 0. 1 and 0 is 0, 1 and 0 is 0, 0 and 1 is 0, but only here it's a 1. Finally, we have exclusive OR, which is either this or that, but not both. So this one takes a 1 value only when they're different, right? Either this, A, for example, or B, but not both. I hope you saw me draw this and I didn't hide it with the camera. Let's just look at an exclusive OR of two numbers. So they're different, it's a 1. They're different, it's a 1. They're different, it's a 1. They're the same, it's a 0. XOR, by the way, bitwise XOR, which is what we're doing here because we have many digits. If you look at one number as a sort of mask, what this mask does is say which digits to negate and which not to. For example, let's assume that, let's assume this was a 0 and this was a 1. And we looked at this number and we say, now let's decide I want to negate these digits, but I don't want to negate these digits. So we put zeros here and ones here. These ones remain the same. This is a 1, this is a 0, because this is 0. Yeah, this is a 0 because 0 XOR 0 is 0. Now these ones I want to negate. So this 0 XOR 1 becomes a 1, and this 1 XOR 1 becomes a 0. That's another way of looking at XOR, which will be very useful in your future life as a programmer and computer scientist. I've covered everything I wanted to cover, and as I said, this will be a very demanding course, but I'm here to help, so don't hesitate to email me, and I hope to meet you soon when you come to Israel. Let's have fun together. Ciao.